get back into it. So right now, so the test is Wednesday of next week. What I'm trying to get done, I'm sure I'll be able to. Instead of having office hours next week on Wednesday and Friday, I'm gonna do Monday and Wednesday. I'll have to figure out exactly when I can hold them on Monday, but I will have office hours Monday. Most likely between class and 2 o'clock, but when I figure out the specifics, I'll put them on Canvas. I'll let you know. So talking about series, we kind of left in the middle of this example here. So kind of had the same question that we had with sequences that we're going to have throughout most of this chapter, which is convergence or divergence. So let's kind of reset the stage here. I have this series, which is given by this formula 2n over 3n plus 5. So first thing I want to kind of get everyone reminded of is what the difference is between a sequence and a series. So in a sequence, you have an ordered list of numbers, ordered list of terms. The thing that makes it a series is that instead of just looking at the terms, we're basically looking at like what the final term or what the terms kind of trend to. I'm looking at what the sum of all the terms tends to. So in this case, I have a sequence of partial sums. So basically, this 2n over 3n plus 5, that formula gives you the sum of the first n terms. So I think I did a couple examples last time. The first term is going to be 2 over 8. And let's be really clear about this. This 8 over 17 that I found, what is that? Is that a term in the sequence? It's, yeah, so that's what I wanted to make sure that we're set on, is that 8 over 17 is not the fourth term of this sequence A sub n. It is the sum of the first 4 terms in that sequence. Don't really know exactly what the terms are. But we know that the sum of the first 4 is 8 over 17. Any questions on that so far? Go ahead.
Why did we use 4?
I just picked a number.
Oh, okay.
Picked a number that was far enough away from 1 that we could think about what's going on. So now I want to know if this sum converges. Basically, if I let n grow larger and larger and larger, is this sum going to converge? Is this sum going to trend towards a number? What do we think? You gonna vote for no? So, what's the thing that represents the sum here? The sum is this formula that I have boxed in on the right, this 2n over 3n plus 5. So basically, I'm asking about the limit of this. What's that? Is it going to go towards 0? I don't think it's going to converge to 0. Could converge to 2/3, because basically, one thing we've done in the past section, if I divide this thing by n over n, or multiply by 1 over n over 1 over n, then I can rewrite this like this: 2 over 3 plus 5 over n. 2 and 3 are constant, but what happens to the 5 over n as n gets big? Goes to 0, so this converges to 2/3. Go ahead.
So for this one is like an n term, like to test for divergence.
Yeah.
If it's other than 0, it would be.
So you're thinking about a little something else. So basically, and it's a very important distinction to make, but let's do this. Let's talk about the first 2 terms of the sequence. Not the sequence of partial sums, just the sequence A sub n. We said the first term was what? 2 over 8. I'll just leave it unreduced. What's the second term? What's that?
4/11.
How'd you get 4/11s?
I just plugged in 2 for n.
You plugged in 2 for n, you got 4/11s.
Oh, wait, but that's not the original.
Right. So here's the thing, I think that's the thing that we're getting hung up on, is the fact that that formula does not give us a term in the sequence. It gives us the sum of that term and all the other ones before it in the sequence. So you plugged in 2 and got 4/11s. So the second term is really 4/11s minus 2/8. And then what's the third term in this formula? 6/14. So that's not the third term, that's whatever's left over after you subtract off those next 2 terms. So because we don't really have, we could build one, I believe, but we don't have a good formula for what the terms of the sequence are. Just for what the final sum of the first several terms are. So because of that, this 2n/3n plus 5, we are not saying that those are the terms of the sequence, that's the sum of all the terms of the sequence. But looking ahead a little bit, what if we did have a sequence? Actually, I don't want to muddy the waters too much. We'll talk about that distinction a little bit.
Why are we subtracting by 2/8 on third term? 4/11s is the sum of first and second.
Oh, okay, thank you. So 4/11s, oh, you're right. 4/11s is the sum of the first 2 terms, right? Okay, so that makes sense. Anything else? Okay. So we've talked about this kind of series before, or at least this kind of sequence before. What do we call this kind of sequence or series?
Geometric.
It's geometric. Why is it geometric?
Very hard to end.
So here's the definition of a geometric sequence. How do I get from A to AR? What do I multiply by? R, right? How do I get from AR to AR squared? Times R. That's called the common ratio. Basically, if I can take some number and multiply it by any term in the sequence to get the next one, as long as that number doesn't change, that's what makes a geometric sequence a geometric sequence. The fact that I have that predictability, that same multiplied ratio from one term to the next throughout. And did we talk about when this thing converges? We talked about when the sequence converges, right? What values of R did we say that the sequence converges on?
From 1, not including 1, or -1, I mean, not including -1, up to and including 1.
Okay, so this is where the sequence converges, right? Do we think this is still true for the series? Will this series, so the sum, will that sum converge for all these values? I see a head shake for no,
Should,
which I agree with.
is it? The, should be -1. Is there equal to?
No, because what happens in the sequence if you have R equals -1? It alternates. So let's just pick a number. If A equals 5 and R equals -1, then your sequence is going to look like this: 5, -5, 5, -5. That's divergence. That's why you include 1. If you just have the same term over and over again, that converges by virtue of it just being constant. So now, if this right here is for the sequence, but I don't believe that the series is going to converge in all those cases. In fact, there's exactly one value I have to leave out here. So if R equals 1, this sequence just looks like this, right? That sequence converges, right? Does that series converge? Why not?
It increases forever.
What increases forever?
The sum.
Right. If I'm adding 5 over and over and over again, there's no way the sum is going to settle in on something. So sequence converges for the values are already listed, but the series has to converge, only on these interior values. It's not including -1 and 1. It'll converge for everything on the interior. Because what's going to happen if R is between -1 and 1? What's going to happen to successive terms?
Towards 0.
They're going to go towards 0. Yeah, that's exactly what's going to happen. So the geometric sequence or series has a common ratio. So basically, that's that value I can multiply by any term in the sequence, and that will yield the next one. So it converges in exactly these cases when -1 is less than R, which is less than 1. And for any other R, the series diverges. So very clear-cut condition on what gives you convergence on these kind of series. Good.
So for the slide before this, the ratio is, the R value.
Mhm.
Is it 2/3 or 2? The one before this?
So is this a geometric sequence here? So the one was 2n over 3n plus 5. The sum was 2n over 3n plus 5, right?
Yeah.
But does that mean that is that a geometric sequence? I don't think it's going to be. And as soon as this comes back to me, I'll try to prove it to you. Cool. All right, so we wrote down these first 3 terms, right? Let's do this. Let's actually evaluate some of these things. So 1/4. Someone tell me what 4/11 minus 1/4 is. (11/44) minus 5/44. And let's just do the third one. Hopefully this is enough. What is 6/14 minus 4/11?
5/77.
5/77. What do I have to multiply by 1/4 by to get 5/44? 5/11? Okay, what is 5/44 times 5/11? 25 over 484. That is not 5/77, right? So this is not a geometric sequence. So the thing I just gave you, that very, very easy condition for the common ratio, only applies to that kind of sequence. So then this is not one of those.
Okay, I just thought that, for a series, we were only looking at the end terms. Like the end term of 2n, 3n plus 5, to determine if it's.
We are in this case because that 2n over 3n plus 5, that gives you the sum of the first n terms. So in this case, that's why we're able to look at that formula itself. All right, so I want to find the sum of all these terms. First of all, let's prove to ourselves that the sum even exists. Does this thing converge? I'm telling you it's geometric, so can we at least verify that? If we're going to say this is a geometric sequence or a geometric series, what do we have to know about it? Or what should we?
It increases by the same amount of time.
Yeah, so I'm going to push back on the word increase just because, I know what you're after, but it might not be increasing, right? In fact, in this one, it's not. So what I'm looking for that common ratio. So any guesses or any ideas on what the common ratio is here?
Negative.
Negative 2/3. and I multiply any of the four terms or any of the terms I've given you to get the next one. So what is negative 10/3 times negative 2/3? That should be 29, right? Good question. Where'd negative 2/3 come from? Right, so because it's a geometric sequence, I can take any two back-to-back terms. I'll pick these last two, but it really doesn't matter. And I know this, 20/9 times r has to equal negative 40/27, right? That's what makes a geometric sequence a geometric sequence. So if I divide by 20/9, what do I get? That's the same as 9/20. So what is that? Negative 40/20 is -2. 9/27 is 1/3. And that negative 2/3, that'll govern any pair of adjacent terms there. So we have r equals negative 2/3. Does this thing converge?
Yes.
Should, right? How come? It converges because our common ratio is contained between -1 and 1. So how do I find the sum of geometric series? If it exists, here's what we do. Basically, it's this ratio here, the first term, which I'll call A usually. I think your book also calls A, divided by 1 minus R. So your first term divided by 1 minus the common ratio. So what's our first term here? 5 divided by what? 1 minus negative 2/3, which is 5/5/3. So what's the final sum? Final sum is 3. So even though there's a never-ending list of numbers I'm going to be adding together, I know that that infinite sum is 3. As I take it to its limit of infinity, it approaches 3.
So the answer would it be it converges to 3?
The sum converges to 3,
Sum
or the sum is 3. Those are both fine.
So for all geometric series, you want to put A over 1 minus.
Yeah,
R.
so, and then I want to be very clear. This formula is only available to you in certain cases, right? What are those cases?
Geometric series.
No, I think more than that. Not often. So this doesn't work for all geometric series.
R is just
Only for convergent ones. And that's the thing I want to point out, because that formula, I could very easily pluck out what the first term and the common ratio are. But if that common ratio is too big, you'll get a number that doesn't make any sense. Any questions so far? How about this thing? Is this convergent or divergent? Is this even a geometric series? I'm telling you it is, but if I didn't tell you that, how would you know?
Just simplify the exponents.
Okay, you want to simplify the exponents? How so? I can't add the exponents. I can't multiply the bases together either.
2 squared times 2n.
2 squared times 2n.
Oh wait, no, 2 squared to the n.
Yeah, so one thing, I think what you were trying to do is this. 2 to the 2n is equal to this. 2 to the 2. But 2 to the 2 to the n. The other one we got to do something a little bit different with, but for now I can do this. 4 to the n times 3 to the 1 minus n. Can I do anything with the exponent on 3?
Times 3.
3 times 3 to the negative n. So let's talk about why that's true. What's x to the 4 times x to the 7?
Let's see.
How'd you do that? You add the powers, right? So we typically go this direction. You, without much thought, you can kind of do that. But what we don't usually do is go the opposite way. We can take an additive exponent and break it down the way we just had it described. So 3 to the 1 minus n becomes 3 to the 1 times 3 to the negative n. Did that help? Is there anything else we can do?
Divide by 3 to the n.
Right, so I can make the negative exponent positive. I can also call 3 to the 1 just 3. Did that help? How?
Now you have a ratio of
What is our ratio? 4/3. And one more thing I'll do to point out here is that 4 to the n divided by 3 to the n, I can rewrite as 4/3. So I have a common ratio of 4/3. What does that tell us? Divergent. No need to figure out what the sum is. But one thing I do want to ask here is, what is the first term of the sequence? How'd you get 4? Okay, and that's what I wanted to be sure of, is that at first glance I've had people tell me the first term of this thing is 3. But remember that n usually starts at 1, and in this case we're explicitly saying that the first term is 1. Not the first term, the first index. Go ahead.
Divergent because the R is greater than 1.
Yeah, so basically r equals 4/3, which is greater than 1. That is exactly why we know it diverges. Go ahead.
How did you establish that 4/3 is the common ratio?
That's a good point. So I see where 4/3 shows up in there, but why is that the common ratio? How do I know that?
Every time you increase n by 1, you're really multiplying by another 4/3.
Right, it's the fact that in this case, I'm gonna be multiplying by 4/3 each time. So let's do this. Let's write out a few terms. First term, like you said, is 4. What's the second term in the sequence? Maybe I should write it like this. 3 times 4/3 plus what? Actually, I think it'll be much simpler if I just write it like this. 3 times 4/3 squared, right? Plus 3 times 4/3 cubed, and so on. So I think I gave that advice last time. If you're ever lost at all about these, write out a few terms and see if looking at concrete terms gives you any kind of like feeling about what the patterns are going to be, what's going to happen. If I were to simplify all these, 3 times 4/3 is 3, right? 3 times 16/9 is 16/3. Is 16/3 bigger than 4? It's a little bit bigger than 5, right? And the next one, 64/81. No, it's not. Oh, whatever 3 times 64 is. So 192/27, which is, it's bigger than 5, right? So we have these terms that as I move down the sequence, I'm getting bigger and bigger terms to add together.
That's essentially just multiplied by another 4
Yeah,
with the power.
yeah. So that is that, and that's exactly why 4/3 is the ratio. Because to get from one term to the next, I'm multiplying by another factor of 4/3. How are we doing?
If it's greater than 1, it diverges to infinity. Is that always?
Yeah. What happens if it's less than 1?
Less than -1, less than -1.
Doesn't really go to negative then because it alternates, right? So you can't really say anything beyond it diverges. And if it's alternating and blowing up, Can't even say, so in this case, it's just increasing. But if it's alternating, you can't really say anything more specific about it.
But still, if it's less than negative one, still.
Still diverges. Yeah,
It
'cause-
has to be less than one, it can't be equal to one in this case, right?
yeah, so if we go back a few, because I think I did an example, but like, what if it's R equals 1? Let's just say A equals 1. Then basically
You're always.
your sum is like this, like 1 plus 1 plus 1. So even though the sequence is all filled with the same term, the sequence converges, the series can't. How are we doing?
So the series doesn't include one of the additive doesn't include what R equals 1 the series does.
Correct. So for a geometric sequence converges if R equals 1. The geometric series does not converge if R equals 1. All right. So I'll give you a second to read this through here. So we're gonna try to build up to a few things here. So I want to find the concentration of this drug in someone's system after let's just do it after the first dose here. So how would I do that? Did I not say what the initial dose was? No, the initial dose is going to be 0.2. Basically, for the first treatment, there is nothing in their body originally, so they're being injected with this 0.2 milligrams. Milligrams per milliliters concentration. So after a day, what happens? %30 remains. I'm adding another 0.2, but really there's 30% of what remains from the previous dose is still going to be there, right? What about the day following that? What's that? Well, I'm just building it up like one dose at a time here, right? 0.2 times 0.3 times 0.3, right? Because there will be 30% of what there was the day before, but that is still, that's incorporating the 30% of what was present from the day before that. So basically you get this accumulated effect, right? What would the next dose look like? What am I adding on top of it there? So I'm still going to administer a dose of 0.2 milligrams per milliliter times 0.3 to the third, right? You've seen the patterns emerging, remember? Yeah. So what was the first thing I asked you about was basically those are the first 3 doses, right? So whatever 0.2 plus yeah. Do we have a number for this? I'm more interested in the fact that we can calculate that, but I know we can get a final simplified number, but I really want to focus on how we got there. What is this looking like as we're writing the term for the sequence down? Is it geometric? If you're telling me it's geometric, then you must have an idea of what the common ratio is. Should be 0.3, right? So if it's geometric, maybe I can write a series like this. So can I define that?
30.
I equals 0.
I'm gonna leave it as I equals 1 because there are other ways to factor for that. I know what you're getting at, because basically the first term is gonna be 0.2, right? And our common ratio is gonna be 0.3. But I think this is what we really need. Because our first term does not include that factor of 0.3.
Says it raises,
How do we know what?
it starts at 0.2.
Yeah, it's the very last piece of information. So basically-
It raises, it just says what it raises by, not what it starts at. Or you just-
That's how I'm getting information, because if there's not, if he wasn't getting this treatment before, then that's basically the initial dose is the same as every other dose.
The way it's worded makes it sound like the dose increases, but that means it raises the concentration of the drug in the body, not the.
Yeah, so that's, okay, that's, yep. Whoever wrote this could have done better. It was me. So, yeah, in terms of like basically, the syringe is the same every day, but it's what remains in the body that makes the concentration in the body different. So this is the concentration after n doses. Basically, I got a formula for it now. This sigma notation, I can plug in whatever. If it's been doing this for 100 days, I can say that n equals 100 and calculate this. But what if he's on this drug for a very, very, very long time? What will that limiting concentration be? First of all, is there going to be a limit? How do you know there's going to be a limit?
R is less than 1.
So R is equal to 0.3, and 0.3 is less than 1. Also bigger than -1. So we should be able to find this limit, right? How do I find that limit? A over 1 minus R. What's my A? 0.2 over. So 0.2 over 0.7, which is 2/7, or 0.286 milligrams per milliliter. How are we doing? Okay. I can write this number as a fraction. But how? So I'm still talking about geometric series. So is there a way to think about this as a geometric series? What is that vertical bar over the 1, 7, 65? Right. So is there a way for me to write this as a sum? And better yet, a sum that is geometric?
2.3 plus.
So here's the 2.3.
Plus 17 times 10.
So plus, for now, let's just say 0.017, right? So that covers this part of the number.
Times 10 raised to
Let's just do this. Let's get the next 1/7. How many zeros do I need to incorporate that? 0.00017 plus 0.0000017. And that'll continue indefinitely, right? Is this a geometric series? We have to be careful because the 2.3 sort of ruins it. So I think if we include the 2.3 as a geometric series, it is not a geometric series. But how about the stuff that comes after? Are the rest of these terms going to be linked by some common ratio? They should be, right? So basically what I'm gonna do this, I'm gonna keep my 2.3, but I'm gonna try to write the rest of this as a geometric series. So in order to do that, I try to talk about what the common ratio is. Just treating the point 0.017 and beyond. Any idea what the common ratio will be between successive terms there? What's that? 1/100? How'd you get 1/100?
like 2 decimal points.
Right, basically, yeah, so to get from one term to the next, you're sliding the decimal point to the left 2 places. Or, the way we talked about it before, you can divide any term by the one before it, and you should get 1/100. So, I believe that I have a common ratio of 1/100. For now, I'll put an I, we might have to alter that, but what's the first term in the sequence?
1.7
1.7?
is the first.
Oh, okay.
term is going to be multiplied by 100.
Gotcha. I'm gonna code it as 0.017 because basically there's a very common formula that I don't want to stray too far from. So we know our first term is 0.017, right? That's the first one listed. We calculate our common ratio as 1/100. So what's a good exponent to put on this if we're gonna have our indexes start at 1? I minus 1. So this is a pretty common template you'll see for geometric series, is that the sum from 1 to n of a times r to the I minus 1. So basically you get the common ratio there, but you don't have to like hide what your first term really is. We get to kind of see it as written. How are we doing? This geometric series we wrote, does it converge? Should, right? Common ratio is between -1 and 1. So let's find its sum. What is the sum of our geometric series? So 0.017 over 0.99. So what does that come out to be? 17 over 990. So I want to write this as a fraction. Where can I go from here? Can I rewrite 2.3 as a fraction? Should be 23/10. How many of you know how to use the fraction feature on your TI calculators? I don't have it. I believe this comes out to 2294 over 990. And however that reduces.
1147.
Oh, just okay, just doubles. Yeah. 1147 over 495. Very obvious fraction, right? But when you have you've seen lots of numbers, when you divide them, they come out with some kind of repeating decimal. Those essentially are geometric series, if you have some kind of repeating behavior. How are we doing? I don't think we did that one. So I have this series here, so we're getting away from geometric series onto some more general things. This is not a geometric series. The new kind of series we'll talk about, but I'm telling you this one converges, and we are actually able to find its sum. So don't really know how this series behaves. What is a good place to start? I know for a fact this has a typo in it. That needs to be a negative sign. So what's a good place to start? I'm actually gonna say no, and I think you'll see why.
It's the limit.
What would the limit tell us?
I don't know.
Okay, and that's one thing I want to point. So if we do take this limit, I think we can do it. The limit as n approaches infinity of 1 over n times n minus 1. What is that limit? 0. Does that mean the series converges to 0? No. So we know the sequence converges to 0, but that doesn't really tell us much about the sum. I think that's a fantastic idea. So let's find the first two terms. So first term should be 1 over 1 times, this doesn't work. I got all kinds of typos in here. Let's start at n equals 2. So 1 over 2 times 1 over 2 times 1, right? Would you believe there's no typo in here? Definitely is. Let's just throw this whole thing out for the thing that I suspect should have been the whole time. Starting over. Right. Let's look at the first few terms. First term is going to be 1 minus 1 over 2, right? What's the next term going to look like? One half minus 1/3 plus. Actually, I'll just write it down. You tell me if you notice anything. Anything jumping out to anybody yet? The subtracted, yeah, so whatever I subtract from one term becomes something I add on the next term, right? Okay. So one thing we're noticing is that these end up doing what? These end up canceling out, right? So basically, if I take a bunch of partial sums, all I'll be left with is that 1 minus whatever the last term is, right? Does that tell us anything about what the sum might be? Is it just 1? So here's what I believe we got here is that if we take this sum here, basically here's what our pattern kind of suggests to us. Is it looks like this. 1 minus, what's the right way to say it? Is it just 1 minus 1 over n? Try to limit this. The limit as n approaches infinity of 1 minus 1 over n. So the reason we're saying that is because basically the 1 is not going to, that first term of 1 is never going to get canceled out by anything that comes after it. So the only things that remain are that first term of 1 and the thing we're subtracting, which is basically going to count up with every value of n. So does that limit I wrote down make sense? Is that a limit we can evaluate? Comes out to be what? So basically, as n gets larger, you're gonna have the 1, and you're gonna be subtracting off these numbers that just diminish in size. How are we doing?
Is that the only way to solve it, or is there,
There are probably others. I'm pretty sure that's the most direct.
but there's like no formula?
There's no such, so here's the thing that, and kind of give you a heads up where we're going. There are lots of ways to tell if a sequence or if a series converges. There are very few sums we can actually find. In fact, I might be lying to you because I don't keep up on this stuff all that well, but I believe this thing right here, we have known for hundreds of years that this thing converges. I don't think we know what it converges to. I don't think we know what the sum is. So one of these things in math where we can prove that it exists, but doesn't mean we can figure out what it is. But like geometric series are like one of the exceptions, and these are another, which I think the book and the wider math community calls telescoping series. Because if you've ever seen like a collapsing telescope, basically that's what goes on in these series, is that all these middle terms basically get annihilated. So the metaphor is the collapsing telescope, which is a pretty old metaphor, but it has survived. How are we doing? Okay. One last thing I want to point out probably for today is that this series here is a pretty fundamental one. Let's talk about the sequence. I think we've talked about this sequence before. Does this sequence converge? Converges to 0, right? So basically, so now if we think about the series that I have written here in sigma notation, if you have this sequence that converges to 0, that means that in the series, you're adding a bunch of stuff together, and the things you're going to be adding to it are going to be getting very, very close to 0. But still, this series does not converge. The sum does not ever settle out on something. So let's take a look at why, and I'll try to illustrate what's going on here. Let's write down the first few terms here. So I get 1 plus a half plus a third plus a fourth. So this is what this looks like, right? So this is going to be a little bit of a hand wavy explanation, but hopefully it's convincing. Basically what I have here is I'm going to group these up by halves. So basically I'm going to group enough terms together so they're at least a half. So this is greater than a half. This is greater than a half. What about a third and a fourth? That's greater than a half, right? And I think the rest of these are all greater than a half, right? Maybe I don't even think I need all 4 of them, but I know that if I take 4 of them, that's bigger than a half, right? So basically the logic is this: no matter how small these terms get, I can always group a bunch of them together and make my sum like significantly larger. Because of that, this thing does not converge. So this is kind of a strange series, but it's common enough that it has its own name, the harmonic series.
Slowly going to infinity?
What's that?
Is it like slowly going to infinity?
Yep, very slowly, but
Is this,
quickly enough.
is this, can you call this one of the P series?
Yeah, it did all the P series is kind of it's a related idea to this. And if you're not sure what the P series is, we'll talk about it in more detail soon, but this is a specific case of it. Basically, this series diverges even though the underlying sequence converges. All right, I got 11 o'clock. I told you that most of Monday would be like a review day. There's a couple more things I have to talk about, but not much. So we'll cover that on Monday, and then, yeah, basically whatever questions you have, bring them on Monday, and we'll talk. I'll either see you in office hours today, or I'll see you next week.